Okay, great. So yeah, Jason, actually what's on the web page is not up to date anymore. So Jason decided to talk about K-cuts on Facebook because said it was thankfully.
Okay, so this talk is joint work with Anupam Gupta and Yvonne Lee. So in this talk, we'll study the K-cut problem. So given a graph, undirected graph, let's say weighted graph, delete the minimum weight set of edges to cut the graph into at least K kinetic components. Okay, so in this talk, we'll think of K as a large constant because this problem can be hard when K is, let's say, linear in n. So I think for this talk, there will be two key players in the problem. One is the cycle and one is the cleat. And you can see that for the cycle instance, the best way to cut the cycle into K pieces is just cut any K edge. And what is special about cycle is that you can cut any K edge of the cycle. So the number of first of all, off is K, but also the number of big cuts is also n choose K. For cycle, as for cleat, it's a much more well-connected graph. So you cannot, for example, cut it into half and expect a small cut. So in this case, the best you can do is just cut off K minus 1 singletons. This has size roughly n times K. And the number of min cuts is also roughly n to the K. It's actually n K minus 1. Okay, so basically, the message is that in some instances, there can be many min cuts. And also, there's kind of two canonical ways to cut the graph. Either you cut it into into K pieces cut into large pieces, or if the graph is well connected, then you cut into then the best way to cut is really to cut off some. Okay, so the main questions we'll study in this talk are first of all, how fast can we compute a K cut? So this is an algorithmic question. And the second one is how many minimum K cuts are there? So the example from last slide showed that it can be n choose K, and we'll show that it's roughly n. Some brief history about algorithms. So the classic Karger's contraction algorithm can be adapted to solve the K cut and the 2K time. And there was some work before this work on slightly improving this running time. In fact, even matching it to the K for unweighted graphs. The top 3 results actually give also extremal bounds on number of K cuts. So prior to this work, number of min K cuts was shown to be slightly less than K. And there has been some work on reducing K cleat to K cut. For example, K cut K minus 1 cleat reduced to K cut. Finally, it's known that 2 approximation is known. Can be done poly time, and it seems hard. I think there's small set extension hardness for 2 answers. Okay, so in this talk, we'll study 2 results. The first one is we can actually solve min K cut in about n to the K time. And second, this algorithm can also enumerate overall cuts, similar to how Karger's algorithm does. And therefore, we also get extreme bound of n. So actually, our template is just going to be Karger's algorithm itself. So in fact, our entire algorithm will just be exactly Karger's algorithm. Instead, we'll have a better analysis. So because of that, we'll start off with Karger's algorithm. And let's first study the familiar setting, which is just min2 cut or just minimum cut. In this case, you just the algorithm just randomly contracts edges into 2 vertices remain. So for example, let's say given this graph, you could just keep contracting random edges and do so until you're left 2 vertices. Now, if you look at these 2 vertices, kind of induce a cut when you kind of map the vertices back into the original. Right? These are the red and white vertices. And the classic analysis of Karger, which we will actually show because we'll need that analysis, is that it finds any fixed min cut with probability 1 over n choose 2. This implies there has to be that many min cuts in total because the events are disjoint. We always have to one. Or at most 1. Okay, so now go into more detail, let's see what happens when there are, when we're starting K cuts. So consider the following algorithm. We'll do the same thing, except we'll stop at 2K in vertices. And you might ask, why 2K and not K? That's for a technical reason. And it'll show up in analysis. So let's actually just quickly do this analysis. So we claim that this algorithm will output the minimum K cut with probability about n to the minus 2K. So let's actually do this analysis. So how does it work? Suppose we're at a stage where there are arbitrary here. We want to upper bound the probability that you do not contract, you contract an edge. Because if you think about it, imagine fixing a min cut beforehand. The ideal setting is we do not contract any edge in the min cut over time. That means that kind of min cut is safe at the very end. So in other words, we want to upper bound the probability of contracting edge. So what is a probability of contracting edge of? Well, let's assume that the graph is unweighted now. So it's just exactly opt over the number of edges. And we'll bound opt by K minus 1 times the average of the smallest K minus 1 degrees. In other words, it's just a wordy way of saying the sum of the K minus 1 smallest degrees. That's really just, that is a valid K cut because as we saw from the clique, you can just cut off K minus 1 singletons. And the bottom here is just a degree bound. It's saying that number of edges equals the number of vertices times average degree over 2. Now you might ask, why did I write things this way? Well, just because at this point I can use the fact that the average of the smallest K minus 1 degrees is at most the average of all degrees. That's why I wrote this way. So you can just kind of cancel those two out and say it's at most 2 times K minus 1 over R. So this kind of answers the question of why did it stop at 2K? It's because this number is, once R is below 2K, this number can be more than 1 and we don't want. So finally, the probability that the opt survives can be written. So you might have seen in the standard Karger's analysis, there's like you multiply all these factors together and things like cancel. But in this talk, we'll just think about it like more analytically. You just think of the product of 1 minus this, which is at most roughly exponential of minus 2K times the harmonic number. And x to a harmonic number is just n to the minus, is just n to the power of this. Actually, let me just write this down because we'll actually stare at it through this talk. As you see, you should if you like examine this this short proof, you'll see that the reason why this 2 pops up, which we want to eliminate, comes from the fact that it's right here, which comes from the fact that it's right here, which is actually like it's the reasons because there's a factor 2 in the connection between total number of edges and average degree. Or number of vertices times average degree, there's a factor 2. That is actually the reason why there's a factor 2. Number of edges. Okay, so let's actually, so this may look bad because in particular, this could be tight. For example, in the case when the graph indeed had K minus 1 singletons being the actual NK cut, and also that, let's say the graph is roughly regular, so all the degrees are also roughly. But let's actually see what happens. For example, in the cycle case, actually we get much better. And the reason is because actually opt is not K minus 1 singletons. In fact, opt is actually cut any K edges, which is twice as good because K minus 1 singletons would give you roughly 2K. You cut k edges, you get k. So you actually get a factor 2 improvement, and actually for a cycle, you actually get it. So there is that's some hope of like this analysis maybe better for certain graph classes. But of course, as we saw from the cycle, here it's tight because of two properties. First is that the min cut was k single, k minus 1 single, and also the graph is regular, so therefore there's no gain from there's no gain from this inequality. But here we'll exploit a crucial property, which is that we'll show that as the Kargar's algorithm evolves over time, you will not always get this worst case scenario. So the key idea is that after a while, most vertices, in the case of a cycle, sorry, in the case of a clique, most vertices will actually have much larger. And actually, let me show you separate set of slides that kind of highlight why this is the case. Okay, so actually let's examine the clique again. So when you run Kargar's algorithm with clique, you contract random edges. Every time you contract an edge, this contracted vertex has like twice the degree. It's like size roughly 2 times. So what does that mean? That means that for the remainder of Kargar's algorithm, we do have this large degree vertex. It has twice the degree, and that's good for us. In fact, if you imagine like running Kargar's algorithm for, let's say, a linear number of steps, then you should expect like a lot of these edges to be contracted, and perhaps like some node may have multiple edges getting contracted. This becomes even larger degree. So you should expect that after a while, most contracted vertices have actually large degree. And because of that, if you repeat the analysis, you'll see that if you look, so the top stays the same because we're looking at a fixed k cut. But at the bottom here, the average degree is like twice as much. If most vertices are, let's say, twice the degree, then the average degree is twice as large. So this cancels this factor 2, and you actually get what you want. So that's the key idea. Okay. So how do we formalize this function? There's 2 main steps. The first is a refined analysis of the Kargar's spline randomized algorithm. So we'll see actually different analysis that lends itself better to more fine-grained analysis. And this setting will allow us to use what's called some like we'll bound the number of cuts using some like extremal graph theory type methods. Okay, so let's actually get more detailed. The second one is much easier to explain. So let's for simplicity define lambda k bar as the average contribution of a component. So opt over fit. Think of it as like the average contribution. We want the number of small cuts. These are cuts in this following range. We'll show that this number of cuts, the cuts of this size, is at most like linear in that. And then we'll show, using this fact and using a slightly different proof outline of Kargar's algorithm, that if G has only linearly many such small cuts, then Kargar's line, the retraction algorithm. Okay, so let's actually begin with property 1, which is we'll study a different view of Kargar's algorithm, which lends itself better to more fine-grained analysis. So imagine the following situation. Instead of contracting random edges in each step, we'll imagine like every edge behaves independently from each other. So every edge will contract with independent probability. So this raises a slight issue, which is what if we contract many edges at the same time? This turns out to be not good for analysis. So what we'll do is we'll like kind of divide the intervals into like infinitesimally small intervals, so that every edge has like a very tiny probability of being contracted, and therefore the probability of multiple edges contract the same iterations. Okay, so we have essentially a continuous view where every edge has like an exponential clock, with rate, with this following rate, which means it will contract independently from all other edges with this probability, where you think of this like a time step. So for example, after one time, every edge will be contracted with probability like well actually will not be contracted with probably like 1 minus this to the power of delta. So 1 over delta. The deltas will cancel, so it's normalized this. Okay.
What's the condition of that criteria again?
Sorry.
Condition of that.
Exponential clock.
The previous slide, the condition. Okay.
Oh yeah, let me.
Okay.
This average contribution. Okay, so why is this good? Well, the claim is first, because the time steps are so small, we should not expect multiple edges to be contracted at the same iteration. So the order in which edges are contracted is still like a random. So therefore, this kind of emulates Carter's contraction. Well, the benefit of this analysis is that now the events are independent. So every edge essentially has like you sample like a random variable from this exponential distribution. That's like when it gets contracted, and these are completely independent on different regions. So with this view, let's actually repeat Carter's analysis, but using this continuous. Okay, so let's say there are vertices remaining at some time. Now here R will depend on time, so slightly, right? Once again, we show that you can show that there are at least R times lambda k bar over 2 edges of the graph. That's just because, once again, think of lambda k bar as like the average degree. The average of the smallest k k minus 1 degrees is at most the average degree. So this is why it's true. And what do we contract? Well, every edge, so we have this many edges. Every edge gets contracted with this probability by definition. So the lambda k's cancel, and we get this many edges contracted in that dimension. Now here's where we use the fact that if delta is like very tiny, we should not expect to contract more than one edge. We should expect either 0 or 1 edges. And therefore, this is like contracting 0 or 1 vertices, depending on whether it's 0 or 1. And these are the same. In general, this is true if like the set of edges is like acyclic. This is always true. It's only when there's cycles does this create a problem. But for us, like because this is so small, it's either 0 or 1 edges.
Sorry. What was the point of the last step again?
This time?
Could you just repeat what you just?
Yeah, this time?
Yeah.
Yeah, so I claim that contracting some number of edges is the same as contracting to some number of vertices, the same number of vertices. Because every time you contract an edge, the number of vertices drops to 1. This is false if the set of edges forms a cycle. But for us, because this delta is so small, we expect it's either 0 or 1 edges. So therefore, that's the hold. So what was the point of all this? It's so that R decreases by, let's say, 1 minus delta over 2 in expectation in delta time. So therefore, after t time, the expected number of edges vertices remaining is a 1 minus this number to the number of time steps. And here the deltas now conveniently cancel, and you get this, and you get the following. Okay. And now you essentially want to set this to be like roughly k. Okay, that's what it's not. So what you want is you want to set the t star to be roughly 2 ln n. That means this is like basically 1. So in other words, you should expect this continuous process to stop at n. And finally, suppose we do set this time. then the probability that a fixed min k cut survives is essentially what is the probability that it gets contracted first time step to the power of number of time steps, which gives you this. And for that value of t, you get n to minus 2. So this is not a completely rigorous analysis because like, you have to show that both this is true and also this is true. But this is kind of like at a high level how you can kind of somehow repeat them. Okay. So now let's see how we can use this continuous view to get something better if we have a special property that there are only a small number of small cuts. So I think it's useful to think about in the clique case. That's a case where we saw that we could potentially get a speed up. These small cuts are only the singletons. And because once you get two vertices, it becomes twice lambda k bar. And that should not. In fact, this will be false if you replace this with 2 because clique case. Because you have quadratic many number double sets of size 2. Okay. So actually let's take a look at these linear number of small cuts. And let's look at how many of them can survive by time, let's say t. Okay. So let's fix one small cut. The probability that it survives by time t is once again, it's actually this where we just here we're using the fact that the cut has size at least this. So for this this bound, we're using the lower bound here. For them. I guess this should have been at most. So why is this good? This is because you should expect all of these cuts to die out by time 1 times ln n, because each one dies out with probably e to the minus p. So what does that mean? So compare that to 2 ln n, which is time when the entire process stops. So in other words, like at the halfway point, we should expect there to be no more small cuts. So for example, in the clique case, at the halfway point, we should expect all singletons to be gone. Okay, so you might ask, well, what about cuts of size less than lambda k bar? Here we use the crucial property that these are cuts at least lambda k bar. It turns out like you can easily show that number of k cuts less than, so number of vertices less than the k degree is at most k minus 1, because if there were k minus 1 of them, then that forms a k cut that's too small. Any questions? Okay, so with these 3 properties, we can actually immediately now show a better bound, at least at a high level. Okay, so let's kind of imagine like what's really going on. So we have essentially, let's plot the time with the number of vertices remaining. And we show that basically at time 2 ln n, we have like basically no vertices remaining. And the standard curve sign analysis was that it was some kind of like exponentially decreasing trajectory, because at every time step, like we had this like expected number of vertices remaining is like 1 minus delta over 2 times the whole 1. So it's like an exponential process. But now let's use the fact 3, which is that by halfway point at ln n, we actually have that essentially all small cuts are gone. What does that mean? That means that all remaining, let's say that all small cuts are indeed like disappear from the graph. Then that means that the graph must have like at least twice the average degree, right? Because otherwise that would have been degree cuts are small.
Sorry, Jason, isn't our goal to find one of those small cuts?
That is true. Yeah, it's a bit counterintuitive. So actually, it cannot be that all of them die out because some of them are distinct, right? But instead we based on most of them.
Okay. Okay.
So think of the clique case, right? Singletons are small cuts. Right? We basically have almost all of them die out by the halfway point, and therefore the graph must have. Because what happens? What matters? The average degree.
Got it.
The average degree essentially is twice. Any other questions? Okay. So basically what it shows is that at time, the halfway point, here, most vertices, then I guess your next suggestion, cannot be all vertices because some of them targets from K, right? So most vertices are double the degree. So for example, in the clique setting, essentially most of the vertices are actually not orthogonal singletons, they're like kind of merged vertices, which have at least double. Okay, so what does that mean? Well, that means that.
Right,
Yeah.
what is that, the vertices is at most and good and factor, does that mean that in the worst case, the number of vertices could be like just one K minus one? But back one is like the upper bound. Back one is like the upper bound number of vertices, but
Right,
then you don't lower bound it, so could it be that the vertices is around K minus one, so in that case, they all have a degree less than K bar.
so, if you assume that a K cut survives, those will all survive, right?
Yeah.
So somehow like, you kind of also need the fact that those K vertices survive. Is that your question?
Yeah, but then like, the second one is the upper bound of the number of vertices.
Right,
And then you say like, because like most K minus one vertices have a small degree and the rest of them have a big
oh, yeah,
degree.
yeah, you sum them up. Yeah, it'll be K plus one, very small vertices,
Yeah.
and then a very tiny number of like medium, I guess, small. Think of these as very small cuts, degrees, and these are small cuts.
And then you want to after that average degree is very big.
Mhm.
But then my question is, back one is the upper bound, so it could be the case that the number is way less than entire.
True, okay,
So then, what if it's right around K minus one, and in that
right,
case,
okay,
the
sure.
average degree is small.
So the answer is like, if it's K minus one, then you're already done. Right, like,
Okay.
if there's K minus one vertices remaining, or like constant times K vertices remaining, then the process stops. Right, because like, your entire goal was to contract until K vertices. So once you're at roughly K vertices, you can just stop. So in the worst case, like, you should think about the worst case is when like the number of vertices remains as large as possible.
So why is back one useful here? Because it's the upper bound.
Right, so okay, maybe I'll kind of draw why it's useful, because once you're at the long end, halfway point, you expect an even sharper decrease. Right, that's kind of like what I'm trying to say. Does that make sense? Sure, okay. In fact, if you like kind of think about, so if this is a geometric process in the worst case. So at the halfway point, you expect that they're very root end first. In other words, like as Xiao pointed out, this could be problematic when K minus one is. I mean, it could be that at this point there's like roughly K vertices remaining. That's possible. I'm not ruling that out. But in the worst possible case, like if the trajectory was as bad as possible, as slow as possible, then you should expect root end. So that's which is much larger. Okay, so this is really saying something. In that case, you're shrinking from root end down to one at a much faster rate. It's essentially double the rate. So you should expand and just stop at 1.1. This turns out what we just stopped at. So actually we should stop at 1.5. So this already shows that. So this is like this first. This is entirely bounding like the when this trajectory stops. Right? And recall that we had a completely separate analysis to show that when a trajectory stops at some point, what is it probably that the min K that survives? So those are kind of like separate. Of course, if you want to show them both are true, then again, like it's not like trivial, but that's like a little. So this gives us like essentially to repeat analysis, you get n to the minus 1.5 K probably the min K that's. But of course, like from this analysis, like we're only taking advantage of speed of a halfway point, right? We should be taking advantage of the speed of the entire way, because even as the fourth of the way there, you're getting some speed up. And in fact, if you take advantage of it everywhere, turns out what happens is you get some kind of differential equation, which really tracks the number of granular vertices. And we kind of essentially solve it and show that with high probability, this trajectory does meet its expectation, or at least at most, or at least its trajectory. And that requires some kind of concentration. Okay, so recall the approach. We had this continuous divergent Carter's interaction, which was good for more fine-grained analysis. And also we had this extremal bound on the number of small cuts. So now let's discuss how we get this extremal bound. Okay, so this is essentially what we want to prove. There's a linear number of cuts of size less than, let's say, 1.99 times lambda k bar. Let's actually sanity check this statement. So for a cycle, lambda k bar is 1 because it's k, the min k cut, which is k divided by k. So in this case, there's actually no small cuts because every cut has size 2. Okay, that's good. And for clique, we see that lambda k bar is like roughly n minus 1 because it's basically the average degree, which is n minus 1. So there are n small cuts, and in fact, this is the reason why this 2 minus actually cannot be replaced by 2, because that would imply that any set of size 2 becomes small, and this is what I have. So this it cannot be. Okay, so to prove the extremal bound, we'll actually use. So how do we? What's one way to prove extremal bounds? So one way is to construct what's called like forbidden sets. So you can think of cuts as like sets of vertices. And you can define a set of forbidden patterns that these sets cannot exhibit. And then show that for any set system that does not contain these forbidden patterns, it must have small sets. So for example, like one example of this is like kind of like VC dimension, where you have these forbidden patterns. We will not actually use VC dimension here. In terms of we'll define our forbidden sets. Okay, the first I think I'm almost out of time. So I think I'll just kind of outline ideas. So first we show that essentially if you take any k over 2 cuts of small cuts, you piece them together, they must occupy less than k occupations. Because otherwise, if you just cut them all together, it would induce a k cut of small sets. This is the first. I'm gonna go through this pretty relatively fast because I'm out of time. The cooler thing we use is actually sunflower plus. We show that if you look at the cuts as a set system again, turns out they cannot exhibit what's called a sunflower with non-empty core and a lot of patterns. Something we show. And finally, we show that if both of these forbidden patterns hold for any set system, then this must have a linear number of sets. So once again, this is like kind of technical and really not like kind of like orthogonal to like this whole k-cut approach. So I think for now I'll just keep it. Okay, so those are the main 2 parts. In summary, we got both the combinatorial and algorithmic bounds of roughly n. In fact, in like a subsequent work, and it turns out this was the journal version, we got essentially n to the k times polylog for the running time, and the combinatorial bound will just n to the k without this middle. That was the final question. Some open questions. We suspect that the cycle should be the worst possible case, which has n choose k number of k cuts. So it's an open question, is that true? It's true for k equals 2, which is min 2 cut. The cycle is the worst possible case, but it's still open for min k cut. And somehow this should maybe, proving this should probably require like a simpler, because our approach is still fairly convoluted and uses some extreme set theory. There should be a simple approach. The second question was open at the time of the first iteration of this talk. It is now closed. It is to get a 1 plus epsilon approximation in essentially called FPT time. This is now closed. In fact, the f of k epsilon is essentially the best possible as well. Third question is, can we de-randomize any reasonable k-cut algorithm? So for example, deterministic and the k-bound silicon. In fact, anything less than n2 basically. And finally, I think which is like the question which is more like most relevant to this workshop is actually the lower bound for k-cut is actually from k minus 1 cleat, which for weighted graphs is n to the k minus 1 hard. So actually there is a gap, which is can you actually bring down the running time down to the k minus 1, which would match the k cleat cut. For example, in case 3, Cheyenne mentioned the problem of 3 cut, where this gives you n cubed, but it's potentially you can get better, maybe any squared or even possible. Right. And note that like this current approach of Carter's algorithm will not actually give you better, because even for k equals 2, it gives n squared and not linear. So actually this approach turns out it's likely you need a different approach to tackle the problem. I think that's all I have. Any questions? Any questions?
This lower bound is from unweighted, right? Sorry. This lower bound is from unweighted.
This is for weighted. I guess for unweighted you can do like matrix multiplication. So I guess the lower bound will be worse.
Yeah, so the next one is
So
can you
for
go to
weight-
maximum for K for
Right.
K cut?
yeah, so weighted k cut reduce the weighted k, and unweighted reduce the unweighted. So I guess in this case I'm really talking about unweighted, where unweighted where if you really get into the k minus 1 weighted k, that would match the lower bound for weighted. Weighted k cut, that would match the lower bound for weighted k minus 1. Does that make sense?
Yeah.
So you can actually think about in the unweighted setting, you can also think about matching the n to the, I guess, omega over 3 times k minus 1 bound for know that things are different for small k, because for example, in case 2, so in case of 3, 2 clique is actually trivial. There's no n squared for k clique. So actually this behaves slightly differently when things are super small. But for general, like, think about large constant k, this is still true. The other question.
Everything you said in the talk also applies for weighted graphs, right?
Right, yeah. It's for real weighted graphs there.
Do I understand correctly that the techniques for weighted graph besides Kuiper-Stein is just tree packing? Is there
Right,
any
yeah,
other-
I think that's basically all there is. So I think, right, I think, right now it's only just carbon interaction and tree packing. It's, in fact, even for problem 3, deterministic, the best we can hope for is into the tree packing, because Carter's is just inherent randomized. I see no way to randomize it. So it seems like tree packing is the way to go for these problems 3 and 4. But I think currently I don't see it would like to do this.
Okay, so I'm Jason. Next one. Was supposed to be the last talk of the workshop, but there's a surprise. Josh agreed to talk about OB, maybe let's say at 11:15. We can have like 25 minutes of break. Do you want to?